This
Okay.
meeting is being recorded.
Okay. So our first speaker in this new year of the seminar is Devarshi Mukherjee, um, who is currently here at IMAS at our university, and he will speak about local cyclic homology. Please go ahead, Dev.
Okay, thanks for the invitation, and it's good to be here finally. Okay, so I will talk about local cyclic homology for, let's say, non-Archimedean Banach algebras. But before I get there, let me talk about local cyclic homology for C-star algebras. Okay, so the usual story goes as follows. Um, Invariants such as Hochschild homology, cyclic homology, and periodic cyclic homology, these are typically badly behaved for C-star algebras. And the reason for this, it's not a precise reason, but more of a philosophical reason. And the reason goes as follows. So periodic cyclic homology is derived from cyclic homology, which in turn comes from Hochschild homology. And the definition of Hochschild homology relies on the existence of certain derivations. And, well, derivations you can think of as non-commutative differential forms. And because C-star algebras are in some sense continuous objects, if you have a commutative C-star algebra, then that's continuous functions on a space. And therefore, derivations are things which don't exist on C-star algebras typically. So instead, to compute, uh, let's say, periodic cyclic homology, one takes a certain subalgebra which has derivations. And this process is called smoothing, and one defines a smooth subalgebra for C-star algebra. But here again, the specific choice of C-star algebra is relevant. So there is no, so if you take a different smooth subalgebra, you might get a different answer for your periodic cyclic homology. And just to give an example of what a smooth subalgebra is, let's take the commutative case. So if you have continuous functions on, say, a manifold, then the smooth subalgebra will be smooth functions on a manifold. So that's the motivating example one should have in mind. Okay. Right. So based on what I've said so far, periodic cyclic homology is not the right invariant for C-star algebras because, again, the embedding of the smooth subalgebra matters. So instead, what one can do is one can define a certain refinement of periodic cyclic homology called analytic cyclic homology. This was defined by Ralf Meyer in his thesis, and it generalizes entire cyclic homology of Alan Kohn. And it turns out that analytic cyclic homology is a well-behaved invariant for C-star algebras. And more concretely, by well-behaved, I mean if you rationalize topological K-theory, then for C-star algebras in the so-called bootstrap class, you get an isomorphism between analytic cyclic homology and topological K-theory, rationalized topological K-theory. Okay, so therefore analytic cyclic homology gives you non-degenerate answers. But again, there is this invariance under smooth embeddings that I had mentioned in the previous slide. And analytic cyclic homology does not have this invariance property either. Now, this is fixed by a slightly more technical invariant, and that's called local cyclic homology, which is defined on inductive systems of Banach algebras or local Banach algebras. Now, the difference is mainly technical between analytic and local cyclic homology. But in most cases of interest, such as a thing called Fréchet algebras, local and analytic cyclic homology coincide. Okay, so we have three invariants. periodic cyclic homology, which is not so well behaved. We have analytic and a local cyclic homology. Local and analytic cyclic homologies coincide. And depending on the case, they may or may not coincide with periodic cyclic homology. It most definitely does not always coincide with periodic cyclic homology. And these are three invariants for algebras with topology, in particular C-star algebras. Okay, now we want to carry over all this that is well known and established to the non-Archimedean world. And by non-Archimedean world, I mean topological algebras where the ground ring is the ring of p-adic integers. Okay, so what we're interested in is these invariants for Banach algebras over the p-adic integers. Okay, but it can be seen in the simplest cases that, well, we don't even need any highbrow derivations argument, but even in the simplest cases,
You froze. Was
okay.
okay. So
This meeting is being recorded.
yeah, we go again.
Okay, at what point of time did
You
I
you
freeze?
you were explaining item 2. That
Item
is
2, okay.
that is even in the simplest cases such as the completion, the
Right,
completion
okay.
city.
Okay, but did I explain why?
No.
Okay, uh, right. So then let me explain why again. Okay, so in the simplest case, which is the affine line, that is the p-adic completion of the polynomial algebra, uh, periodic cyclic homology gives you bad results. And what do I mean by bad? So this is a one-dimensional algebra. And in this one-dimensional case, periodic cyclic homology is computed by the X complex, which gives you the algebraic de Rham cohomology. And now for technical reasons that I'll get into later, uh, what happens is that in this case, the de Rham cohomology is infinite dimensional. So you have something which is contractible that you're inputting to your invariant, and you're getting something infinite dimensional. And this is something that you don't want. You just want it to be supported in degree 0, where you want to see your base field, but you're getting infinite dimensional things. So that's what happens when you input contractible things to periodic cyclic homology in this straightforward way. Okay, so instead what you can do is you can do something that is also done in the C-star algebraic case. You work with certain smooth subalgebras. And when you work in this subcategory of smooth subalgebras, then periodic and analytic theories get better answers, as in the C-star algebraic case. I will define what I mean by smooth subalgebras, but at the moment, I just want to state that you can't do the simplest thing, that you can't just put in p-adic completions of algebras you care about, put periodic cyclic homology and expect to get nice answers. Okay, and right, so when you go from Banach algebra to some smooth subalgebra, you again want some kind of invariance under this passage, the smooth subalgebras. Okay, so this is the motivation or the goal of this project. Okay, so now because one might not be so familiar with this p-adic world, let me just say a few things about the objects that we're working with. Let me start by talking about what a Banach space is in this context. Okay, so what you start with is a module, just an algebraic module over the periodic integers. And what we'd like to now define is a non-Archimedean seminorm, which is just a function, a non-negatively valued function, which satisfies the scale invariance and what is called the strict triangle inequality. Strict triangle inequality is the second point, that the norm of the sum of two vectors is at most the maximum of the norms of the two vectors. This is basically what distinguishes non-Archimedean geometry from, let's say, complex geometry. Okay, so this is what a non-Archimedean seminorm is. Now, when a seminorm is non-degenerate, that is, the norm vanishes if and only if the vector was 0 to begin with, then we call this a norm. And a Banach ZP module is a complete normed ZP module. Okay, so the most basic example is the p-adic integers with its p-adic norm. Obviously, you want your ground ring to be a Banach space. And the p-adic norm is given by the p to the minus of the p-adic valuation of the p-adic integer. And the p-adic valuation is defined by the highest power of p which divides x.
Isn't that always a seminorm in any module?
Yes. Yeah. So in general, you just this coming to this. So in general, this is always a canonical semi-norm. So if you start with any torsion-free ZP module, then you can define this canonical semi-norm on it, which is given in exactly the same way. Okay, and now with this, it could turn out that this is just a semi-norm, but if it is a norm, then your torsion-free ZP module is a Banach ZP module if and only if it is p-adically complete. So now this gives us a recipe to construct Banach spaces. And the way you do it is as follows. You start with something torsion-free over your ground ring. You p-adically complete it. And then you give it this canonical seminorm. And that gives you Banach spaces. Okay, and
one question. So when you said, with this norm, it's okay. Not.
Yeah.
So a module, a CP module with some norm that is not the canonical one, could be complete in that norm without being p-adically complete?
Yes. Yes. Okay. Right. So now let's talk about this category. So we can now talk about Banach spaces as a category. So its objects are Banach ZP modules, and its morphisms are bounded linear maps. And this is a closed symmetric monoidal category. It is symmetric monoidal with respect to the completed projective tensor product. And it is also a quasi-abelian category. Quasi-abelian, if that means something to you, then you would know that this is a good setting to do homological algebra, which is typically in algebraic geometry, that's typically done in the context of abelian categories. But this is only a quasi-abelian category. And that does not matter too much because a quasi-abelian category always embeds fully faithfully into an abelian category. Okay, so that's only if that means something to you.
Sorry, you include torsion modules in your category?
No. not in the category of Banach ZP modules.
Because as you define them.
Well, because it's a norm, so you can't.
Yeah. Okay. Yeah.
Right. Okay. So now a Banach algebra are just algebra objects internal to this category. Okay. Or, well, if you don't want to think of it categorically, it's just a Banach algebra the way you usually think of Banach algebras. It has a multiplication which is bounded. Okay, now let's take some examples of Banach algebras. There are two classes of examples I have in mind, one which comes from algebraic geometry, and the other which comes from non-commutative geometry. Let me first talk about the ones from algebraic geometry or rigid analytic geometry. So in algebraic geometry, your building blocks are polynomial rings or quotients of polynomial rings. You then take the spectrum, the prime ideal spectrum of a quotient of a polynomial ring, you glue them together and you build schemes. In rigid analytic geometry, you take the Tate algebra, you mod out ideals, you take the maximal ideal spectrum. This is an affinoid space, and then you glue them together to get rigid analytic spaces. Okay, now what are Tate algebras? A Tate algebra consists of power series, as you can, of this form, where the coefficients converge to 0. And this is a Banach ZP algebra with the so-called Gauss norm. So you just take the maximum of each power of the coefficients of these power series. This is a Noetherian ring. So every ideal is finitely generated and therefore closed. So therefore any quotient is also a Banach algebra. And these are called affinoid algebras. This is the algebraic side of things. The geometric side of things, as I mentioned, you take the maximal ideal spectrum and then you glue them and you get rigid analytic spaces. Okay, so this is a big chunk of examples which come from algebraic geometry. Now let's talk about algebras which come from non-commutative geometry. So what you can really do is, whenever something has some algebraic basis like Leavitt path algebra or a cross product algebra, let's say of a finite group action on some affine variety, or let's say a monoid algebra with a twist, what you can do is you can take its p-adic completion. So that gives you Banach algebra. On the other hand, if you took the C star completion, you'd get the corresponding C star algebra. So for instance, for the Leavitt path algebra, you'd get a graph C star algebra. For certain twists of certain monoid algebras, you would get things like the non-commutative torus. And similarly, you can get the cross product C star algebra by taking suitable C star completions. And then the fourth one is an interesting example that's not due to any work that I've done, but it's in a paper by Andreas Thom and his student Anton Klausnitzer. That paper defines the p-adic analog of a Hilbert space, which is denoted by this QP of X, which is a certain topological abelian. It's a locally compact ZP module. It's not yet a vector space. And then there is a way to define bounded operators on such a p-adic Hilbert space. And it turns out that it has the right K theory. So it has the right K0 and K1 group. And it gives what you want from, let's say, the Kalkin extension and so on.
So
this
so
is what
zero.
that paper does.
So you
Yes,
mean
yes.
the right is everything is zero. Okay.
Yeah. So this is what that's a recent paper which think one should investigate, and in particular, one can define things like, well, continuous functional calculus is one of the things that could be defined using the approach that's given in that paper. And well, and the idea of all of that should be that one can also define C-star algebras in that context. But anyway, that's not work that I've done, but it's work that could be done to get more classes of non-commutative algebras that are at p-adic analogs of things that people otherwise consider in non-commutative geometry. Okay, so these are Banach algebras in non-commutative geometry. Okay, so hopefully I've given you enough examples of algebras which arise in this p-adic setting. Now let's get back to the question of cyclic homology for Banach algebras. Okay, well, let me first give some more background on what we want from such a cyclic homology theory. And before that, let me again talk about the algebraic and the complex case. So to begin with, cyclic homology is an invariant of associative algebras, and periodic cyclic homology generalizes de Rham cohomology for smooth manifolds, and Hochschild homology generalizes differential forms on manifolds. More concretely, one of the things we expect a non-commutative invariant to have is that when we restrict it to an appropriate version of smooth algebras, then it should give us the right de Rham theory. So if you take periodic cyclic homology of smooth functions on a manifold, then it gives us de Rham cohomology made to periodic. Or in the algebraic setting, if you have a smooth variety of a field of characteristic 0, I think I made a typo there. X should be the spec of A, and A should be the ring of the coordinate ring of X. Okay, then HP of A should be the algebraic de Rham cohomology made to periodic. So this is what exists in the characteristic 0 or the complex setting. Now in characteristic P, the right de Rham theory is rigid cohomology. This is not something I'm going to define explicitly, but it does the same thing that algebraic de Rham cohomology does, but in this characteristic P setting. Okay, so the first question is, what is the right non-commutative theory generalizing rigid cohomology? This is kind of the first point one should start any kind of non-commutative geometry with. Okay, but before I answer that question, let me say a few more words about the category we should work in, which is also related to the first slide of this talk, which is working in a smooth subalgebra rather than with Banach algebras directly. So as I had mentioned right then, we can't work with Banach. We can't plug in a Banach algebra and periodic cyclic homology on it and hope to get interesting things. Again, the reminder is this, if we take the affine line, then we get bad answers in de Rham theory. So now what do we do? So what we want to do is we want to take something in between the polynomials in one variable and the p-adic completion. And this is called the Monsky-Waschnitzer algebra of the polynomial algebra. It turns out that this algebra is kind of defined such that it has the right, let's say, analytic type, such that differential forms are well behaved, and you get the right de Rham theory. So this should be the type of algebras that one should consider in defining invariance on things, well, let's say either over torsion-free algebras or algebras with torsion. if you start with algebras with torsion, then obviously you have to lift to a torsion-free algebra, because there's, again, nothing reasonable you can do working over, let's say, a finite field. Again, de Rham theory is badly behaved there. And the right lifting that goes back to Monsky and Waschnitzer is this kind of algebra of analytic functions with just the right growth properties. And again, I'm not going to define this very explicitly, but just think of it as something sitting in between the polynomial ring and its p-adic completion. But again, if you know what these words mean, then this is the algebra of functions, of analytic functions, which are
There we go.
This meeting is being recorded.
okay. Right. As I was explaining, if we now take any smooth finite type commutative ZP algebra, and we take this Monsky-Waschnitzer completion, then the periodic cyclic homology of this Monsky-Waschnitzer completion gives what we expect it to give, which is a periodified version of the right de Rham theory, and that is rigid cohomology in this case. Okay, so this is the right subcategory of smooth algebras that one should consider. Okay, now let's delve a bit deeper into this subcategory now that we know that HP gives the right thing. These algebras are called Dagger algebras, algebras of the type of Monsky-Waschnitzer. But it turns out we can define this in a coordinate-free way, that is for a non-commutative algebra as well. We can define this kind of growth completion. So the way to define this growth completion would be through bonological analysis. I won't get into that for this talk, but the idea is that you can define power series with some controlled or with some pre-specified way to control its radius of convergence. And here I mean power series in let's say non-commutative variables. So that's the way you would define a Dagger algebra in the non-commutative world. That's been done by in a paper with Ralf Meyer. Okay. So, but the important thing to note is that these are just complete torsion-free and ZP algebras, but with certain properties, with certain growth properties, which we call semi-Dagger algebras. Okay. Again, back to our study of Banach algebras. Any Banach algebra can be turned into a bornological algebra simply by using its norm. And it turns out that with this norm, if we equip a Banach algebra with this bonology, then any subset of this Banach algebra is bounded. So therefore, in particular, it is also a Dagger algebra. So the only point that I would emphasize here is that Banach algebras are sitting in this category of Dagger algebras. You don't even need to know what Dagger algebras are, but it contains all the algebras that I've mentioned and all the algebras that we care about in this talk. Now, this category of Dagger algebras is, well, it's large enough that it contains Banach algebras, but it's not too large in the sense that we can control the invariance that I'm going to talk about. So in particular, it would not work um, if we took just complete and torsion-free algebras. We do need this growth property stuff to well, it's a really subtle point, but we do need it for the analytic cyclic theory to work properly. And I can clarify that later on, if you ask. Okay, so now before I define local cyclic homology, let me talk about analytic cyclic homology again, as in the complex or the C-star algebraic case. There was this intermediary invariant that was defined, which has better properties than periodic cyclic homology, but does not yet work for Banach algebras. Okay, so in a 2020 paper, we constructed a functor from the category of complete torsion-free ZP algebras. So the largest possible category of torsion-free algebras to QP vector spaces. And this functor satisfies homotopy invariance, excision, and Morita invariance, in particular also matricial stability. So this is just a functor that we constructed. And then subsequently, we also constructed a functor in the torsion case, that is for FP algebras. And this functor also satisfies these properties. It satisfies homotopy invariance, excision, and matricial stability. So that's analytic cyclic homology. A few more things about analytic cyclic homology. The way it's defined, I'm not going to define it, but I'm going to talk about the way it's done in a more moral way. So the idea is that you take an FP algebra, you lift it to a torsion-free algebra, and you take its Dagger completion. And then you apply a certain tensor algebra construction, and then you take what is called its tube algebra, you base change it to QP so that you have homotopy invariance, and then you take its Kunz-Quillen X complex. And that defines the theory. But the point is that we lift things from the torsion case to the torsion-free case, and we take this Dagger completion. And importantly, what we showed is that it does not matter which lifting we choose. So you can take any complete torsion-free module lifting and do this tensor algebra and the tube and the X complex construction. And it does not matter which lifting you choose. And note that such a lifting always exists. You can just take the free module generated by the base algebra. That's something that is by construction complete and torsion free. And then you can take its tensor algebra and so on. And then finally, you take its Dagger completion. Okay, and an example, well, let's say a sample computation from algebraic geometry is that for smooth curves, that is one-dimensional varieties over a finite field, the analytic cyclic theory gives you the same thing as rigid cohomology of the variety. Okay, now an important result is that if your lifting is such that it's a Dagger algebra, which mod P gives you the algebra you begin with, and if this algebra has the fine bonology, then the analytic cyclic homology of this lifting, as in this first functor, coincides with the analytic cyclic homology of the algebra over the residue field. that is the second functor. Okay. Now, I gave you a computation for commutative algebras. Let's take a non-commutative algebra, such as a Leavitt path algebra. So if you take a graph, you take its Leavitt path algebra, you can turn it into a bornological algebra, a complete bornological algebra in a trivial way. That is, you give it the fine bornology. Then the analytic cyclic homology of the Dagger completion of this Leavitt path algebra by this theorem above is the same thing as the analytic cyclic homology of the Leavitt path algebra, but with coefficients over a finite field. And the latter corresponds to certain, well, in degree 0, it's the co-kernel of the incidence matrix. In degree 1, it's the kernel of this incidence matrix.
One question. So your homology theory B, the second homology theory defined for FP algebras. So it's for algebras without any bornology, or if you will, the bornology is the fine bornology.
Yeah, precisely.
So that the theorem in this slide says that that D is a lifting of the bornological algebra you are considering, which has the fine bornology. If not, it's not a lifting.
Yeah. It's not an admissible lifting for this theorem.
Yeah, it's not a bornological lifting. If the bornology is not a bornology it can't, then okay.
Yeah.
That's it.
Okay, so these were some computations of analytic cyclic homology. If you didn't follow anything, just take away that if you take a Leavitt path algebra over a finite field without any bornology or anything of that kind, then you get exactly the computation you get in the, well, let's say the K-theory case and so on, or the periodic cyclic homology case. Well, base change to QP. Okay, now, again, as a reminder, we'd like to talk about p-adic completions and Banach algebras. Now, these Dagger completions that, let's say, of this Leavitt path algebra from the previous slide, this is not a Banach algebra with that bornology. This is not a Banach algebra at all. And general Dagger completions of torsion-free algebras are not Banach algebras. So what we'd like to compute are invariants of Banach algebras, which reduce mod P to something in the fine bornology. And then let's say to compute that invariant, we take a lifting, which could be the Dagger completion of some torsion-free lifting. So on one hand, you have this Banach algebra, which reduces mod P to something reasonable, that is with the fine bornology, and which also lifts to something reasonable, where by reasonable I mean a Dagger completion. Because for Dagger completions, our theory is well defined. Now, how do we define such a theory which achieves all of this in combination? This requires a slight trick to change the bornology on a Banach algebra. And it will turn out that it changes nothing about the properties of the Banach algebra. It's just a very subtle trick which achieves this this reduction to something reasonable, reduction mod P to something reasonable. Okay, now what is this bornological maneuvering that I'm talking about? That's achieved by what is called the compactoid bonology. So let's say you start with a torsion-free ZP module, a bonological ZP module. We call a subset compactoid if there is a bounded submodule such that for any n, there's a finite subset such that S is contained in the module generated by this finite subset plus a power of p times t. So, well, what this equivalently says is that a, a subset is compactoid if there is a bounded submodule which contains it, such that if you take its reduction mod p, then you get exactly the a finitely generated module. So in particular, obviously what this achieves is that the reduction mod p of of a torsion-free module with the compactoid bonology is the fine bonology. Okay, but before I get to the properties of this new bonology, let me remark that these things have been studied in the, well, both over the complex numbers and over QP in topology. So for, let's say, locally convex topological vector spaces, the compactoid bonology, or the pre-compact bonology as it's called over the complex numbers, are, let's say, bornological analogs of the pre-compactoid topology, or the compactoid topology, or the relatively compact topology. So these are things that have been studied in topology previously. Okay, now the properties of this bonology. So if you start with something torsion-free again, then mod p, this has the fine bonology. This is pretty much by construction. If the module is bonologically torsion-free, then equipping it with the compactoid bonology does not change that. And likewise, if your module is complete, then the compactoid bonology is also complete. And if you put these three properties together,
This meeting is being recorded.
okay, so now let's study the properties of the compactoid bonology. So if we start with a torsion-free module, then pretty much by construction, its reduction mod p has the fine bonology. That is the bonology generated by finitely generated submodules. If your module is bonologically torsion-free or complete or semi-dagger, that is, if it has these growth properties, then the compactoid bonology inherits all these properties. It inherits torsion-freeness, completeness, and the linear growth property.
So, would it be fair to say that, I mean, a bornologic, so a Dagger algebra has the compactoid bonology if and only if mod p to the n for all n, it has the fine bonology, the reduction mod p to the n.
Yeah, I think so.
So that one could consider, I mean, a new class of Dagger algebras, Dagger prime. And yeah.
Yeah.
Okay.
Yeah. Well, so mod p to the n, it always has the fine bonology. I guess the thing is about the converse. That is, if something is mod p to the n fine for all n, then, and if the original algebra was complete, then
And Dagger.
whether, yeah, and yeah, okay, yeah, then it's true. Yeah. Okay, so now the only kind of definition for today is that if you treat HA as a black box, it is just this functor which has these properties, then local cyclic homology of a Dagger algebra is defined as the analytic cyclic homology of this Dagger algebra with the compactoid bonology. So that's just the definition of local cyclic homology. Now you can also totally forget about what a Dagger algebra is. You can plug in a Banach algebra over there. So the local cyclic homology of a Banach algebra is the analytic cyclic homology of the Banach algebra with the compactoid bonology. So what you're still caring about is a Banach algebra, but you're kind of using this black box analytic cyclic homology functor, and you're applying that to something with some bit of bonological trickery. But you need to know none of that. You just need to use the formal properties of HA. And just using this this small trickery, we have this we have a proposition which kind of combines what I previously spoke about. That is, you want to talk about Banach algebras, you want to reduce them mod P, and you want to lift them to a Dagger algebra. And that's kind of the class where analytic cyclic homology is well behaved. And this is the proposition which makes that precise. So if you have two Dagger algebras, in particular Banach algebras, that reduce mod P to the same FP algebra, then the local cyclic homology, without further assumptions, the local cyclic homology of the two Dagger algebras are the same. So this gets rid of any of this fine bonology assumption that's kind of hidden in the definition of local cyclic homology. So in particular, if you start with this Banach algebra and you have a Dagger completion of the reduction mod P, then the local cyclic homology is the same for both these algebras. And okay, so short kind of proof is that so you take these two Dagger algebras, D1 and D2, by the lemma that I had pointed out previously, this one, in particular the last point. You know that D1 and D2 prime are both Dagger algebras. And well, by hypothesis, they are isomorphic mod P. And this does not change if you apply this prime functor. And importantly, the prime functor, if you reduce it mod P, it has the fine bonology. So in particular, what you have is that the analytic cyclic homology of D1 prime is the same thing as the analytic cyclic homology of A. And that's the same thing as the analytic cyclic homology of D2 prime. And both these analytic cyclic homologies are by definition local cyclic homologies. So that completes the proof. Okay, now finally the formal properties of local cyclic homology. It is homotopy invariant with respect to periodically complete the periodically complete affine line. And this kind of corrects what I had posed at the start, that HP is not at all well behaved for the p-adic completion of the polynomial ring. But this turns out to be the right homotopy type for local cyclic homology. So the local cyclic homology of a Banach algebra, say, is the same thing as the local cyclic homology of the Banach algebra tensored with the p-adic completion of the polynomial ring.
A little question. What is the prime of the p-adic completion of the polynomials? Is it the Dagger completion?
That's which prime?
So you take this CP of T hat, right? You take the
hat.
Hat. You take the
Mm-hmm.
the compactoid Bonology of it. I mean, the prime functor that you, and what do you get?
Right.
Do you get the Dagger completion? Oh,
no, you don't.
But you still get something that has the analytic cyclic homology of CP.
Yeah. And again, the way to see this would just be you tensor with FP. So reduction mod P, this would be d mod P tensored with FPT. So that's just the usual polynomial homotopy invariance. And then you lift it to the Dagger completions. And you also use some other properties of the compactoid Bonology, which I'm hiding. For instance, the prime functor is exact, and it also commutes with tensoring. So these were things I did not really talk about, but those are all things which are kind of used in the proofs of these little propositions. Did I freeze? No, I did not freeze. Okay.
No, you're fine.
Okay, great.
Rush before you freeze again.
Yeah. Okay, then there is matricial stability again, which is just the same result, but you take the p-adic completion of the matrix algebra, and that gives you the same thing as the local cyclic homology of your Dagger algebra. And finally, it satisfies excision. So if you have an extension of Dagger algebras, or if you have an extension of Banach algebras, without necessarily bounded linear splitting, so it is just any extension of Banach algebras, then there is this induced exact triangle. This is a key feature of this compactoid Bonology functor that we don't need to talk about semi-split extensions. The compactoid Bonology functor is exact, so you just apply prime to this extension, and then you take its reduction mod P. It has the fine Bonology. Use the excision result for analytic cyclic homology for algebras over the residue field. So you get an exact triangle there, and that lifts to an exact triangle at the level of analytic cyclic homology. And that's the same thing as the local cyclic homology. Okay, so we have defined this functor which satisfies homotopy invariance, stability, and excision for Banach algebras. Okay, and well, this is kind of like a roundup of things I've been saying anyway. So if you now start with some ZP subalgebra of a Banach algebra, so any ZP subalgebra of a Banach algebra, and if you see that such a subalgebra and this B, so if R and B have the same reduction mod P, then the analytic cyclic homology of the Dagger completion of this algebra is the same thing as the local cyclic homology of the Dagger completion. And that's the same thing as the local cyclic homology of the Banach algebra. Okay, now what does this mean? In rigid analytic geometry, what this means is that you can use Banach algebra liftings to compute rigid cohomology or the right DRAM cohomology. The last point is it's slightly more speculative, but it has all the right analogs in over the complex numbers. So if you take, let's say, a representation, rho A, of some p-adic Lie group, then you can define a certain subalgebra of analytic elements of a continuous representation, let's say. Then it's natural to ask what is the relation between the subalgebra of analytic elements and the representing algebra, the continuous algebra, let's say. And this kind of a theorem would, for instance, say that that the local cyclic homology of analytic elements of a representation give you the same thing as the local cyclic homology of the representation itself. And well, this is again not a complete story, this part, but in let's say the complex case, or in what is in the study of local Langlands correspondences, what one studies are let's say reductive p-adic Lie groups, or let's say GLQP or something of that kind. And what one wants to do is, well, let's say you represent it on a complex bornological vector space or some complex topological vector space. Now, there are some algebras which can naturally be associated to such a representation. One of them is, of course, the reduced C-star algebra. Then there is also the Schwartz and the Hecke algebras. And it turns out that these three things are related by, well, the reduced group C-star algebra, the right relation on it, or the right invariant on it, is topological K-theory. And that's isomorphic to the periodic cyclic homology of the Schwartz algebra. And that's isomorphic to the periodic cyclic homology of the Hecke algebra. And this is used to kind of provide a simpler proof to the Baum-Kohn conjecture for such groups. So there could be, yeah. What? Sorry?
Injectivity. So that will be Novikov.
Yeah.
I mean, these proofs using homology always are good to prove injectivity.
Right. So yeah, these are kind of analogs I would expect in the p-adic world as well. One would, of course, have to, well, at the moment, I don't know if there is an analytic Baum-Kohn conjecture, but if there is one, then such tools would be useful in dealing with analytic Baum-Kohn conjectures. But okay, this part of the story is very far from complete, but it's something that can be done in the future. Okay, so a summary is that what we've defined is an invariant of Banach algebras, which satisfies excision, homotopy invariance, and stability. This invariant is completely determined by its reduction mod P. And finally, we can also do certain computations. We can compute p-adic completions of Leavitt path algebras. We can compute Laurent polynomials and variables. Again, yeah, the usual one-dimensional variety case that I pointed out. Okay, yeah, these are the computations that I think we've done in that paper. Right, so with this, I would end my talk.
Okay, thank you very much. I just want to make an assertion and then I leave because I have to fetch my child from Taekwondo. So example 6.4 of our joint paper says that analytic cyclic homology is invariant under tensoring with the p-adic completion of the matrices. So this particular property is already enjoyed by Analytic.
Right. Mm-hmm.
Okay.
Yeah.
So Eugenia is the host now.
Mm-hmm.
So I leave you with her and I stop the recording.